So another way of representing this is as follows. Imagine that we have this random sample I'll call SK, and there's 1 to capital N of them, some large number that we generate. And let's let NJ denote the number of stock of my samples that equal the jth price in the binomial lattice. And we'll write that as S0 U to the J D to the N minus J. So, and so these NJs are defined from 0 up to little n, right? Because we have little n plus 1 stock prices at the end of our lattice. And if we look at all of these capital N generated stock prices, we can sort them into buckets and define capital NJ as the number of our generated stock prices, which happens to equal this jth stock price. So the formula I gave a minute ago for this estimate, I'll put a cap on it, a caret, just to denote that this is an estimated price, not a price that comes from our binomial lattice, is a present value, e to the minus r time interval. And instead of the original way I wrote it was 1 over n times the summation of the call function evaluated at sk, and then I would add this up from k equal 1 to capital N. But now if I put all of those stock prices into my buckets, I can rewrite this. There's going to be any number. It's going to be a lot of duplication. I can now convert this summation from 0 to n, and I have NJ C with the correct stock price, S0 U to the J D to the N minus J. So let's make sure this makes sense. What I've done is simply say NJ are the number of generated stock prices that equals the jth price on my lattice. And so I've now converted the summation from my sample to a summation using the original lattice prices. And now if I look at this and I bring the n inside, the question really becomes, is NJ divided by n approximately equal to the probability I want? Namely, what probability is it that I want? Well, it's the probability in my original formula. If I look at the percentages, the percentage of my generated stock sample that equaled this jth price, is that and that's what NJ over N is, right? It's the percentage or the proportion of my sample that's equal to the jth price on the lattice. Is that approximately equal to that probability? And your instinct would be, well, of course it has to be approximately equal to that, because that's exactly what it means when you generate a random sample. It means that every stock price in the distribution occurs, in the theory, with exactly this probability, and so in our sample it's going to occur with approximately this probability. And in fact, we can formalize this using a multivariate distribution, which is outside of the scope of this test, but this can be formalized, and that is, it turns out these capital NJs are random variables that follow a multivariate probability distribution. And in fact, it is the case that these proportions equal that. In fact, the expected value of this proportion is exactly equal to this expression. So the reason I can generate this random sample and take the average payoff in place of the expected value of the payoff on the lattice is precisely because when I'm generating random samples, those samples carry with them the appropriate probabilities of the outcomes I'm interested in. And when I take that average, the average converts into an approximation of the expected value. And this is really no different than any kind of sampling where one samples from a probability distribution, averages the values, and expects that you will have developed an estimate of the mean or the expected value of that distribution. That's all that this is.